We're going to look at the history of the atom from 2,000 years ago till today. We'll look at a few of the gentlemen that gave us the history of the atom and where it has come from. Okay, we'll start with our friend Democritus, 460 to 370 BC. Democritus was Greek. He was one of those famous Greek thinkers along with Aristotle and Plato. So we really don't even think of this as chemistry, but Democritus just started thinking through, hey, all this stuff, dirt, my house, this wine I'm drinking, whatever, it consists of something smaller, right? Individual parts that make it up. And he called that word atomos, and that's where we get our word for atom. Atoms are indestructible. Now, he was kind of wrong on this, right? But he didn't know 2,000 later that scientists would be splitting an atom. He said that atoms are solid, but also invisible. Now, maybe he meant not visible to the eye, but atoms are solid, and he would just call them a round sphere with no internal parts, something like this. So very simple, straightforward. Again, he didn't have a lab to go in and do experiments. Democritus was really just thinking. This was more of a lesson on philosophy than it even was on chemistry. So that's where we start with Democritus. And then we can go to our friend John Dalton. Notice a lot of years have passed. Dalton came about in the Enlightenment when people started again thinking about deeper things in life, science, obviously. So Dalton gave us the atomic theory of matter, and this said all elements are composed of atoms. This is Democritus, are composed of atoms. So all bigger things are made up of smaller things. All atoms of the same element are alike. He said that hydrogen or oxygen, take whatever you want, he said that all oxygen atoms are the exact same. And we're going to find out that is not the case as we go forward, because we'll talk about this word as we move forward, isotopes. Isotopes make that not the case. Moving forward, atoms of different elements are different. Well, that makes sense. So hydrogen is not like carbon. Carbon is not like oxygen, right? Atoms of different elements are different. And atoms are not created nor destroyed. He didn't exactly give us the law of conservation of mass, but he was thinking through this. So in a chemical reaction, we can't just have things created. We can't just take things and destroy them and move them out. Atoms are not created nor destroyed. And importantly, atoms combine to form compounds which have the same relative numbers and kinds of atoms. What does that mean? Really simply, so if we're taking CO2, a molecule or a compound of CO2 is always going to have one carbon and two oxygen, right? If we have CO3, well, guess what? CO3 is not CO2 because it has 3 oxygen, and CO2 has 2 oxygen. Again, very simply thought, but pretty profound for his day. And John Dalton's model of the atom is just like Democritus, solid sphere. He didn't know anything about protons, neutrons, and electrons. It's solid, it's sphere, no internal parts as well. Okay, moving on. Our friend J.J. Thompson, 1856 to 1940. J.J. Thompson discovered the electron via the Cathode Ray Experiment, and we'll talk about that a little bit later. His model we call the plum pudding model. In America today, we would refer to this maybe as the chocolate chip cookie dough model. We're not real familiar with plum pudding. He also discovered isotopes in 1913, so he's a pretty influential guy. He gave a lot to chemistry. So I like this. This is the plum pudding model. And what do we have here? We have a solid sphere, and that solid sphere is positive. Its charge is positive. And then all around, you see, we have little dots, chocolate chips, if you will, of negative charge. And these would be the electrons that Thompson discovered in this cathode ray experiment. And you see the cathode ray experiment down here. We'll go back to that. You see the cathode ray experiment right here. And we see an anode, we see a cathode. This yellow line that you're seeing is negative charges. And what happened was that as he put an electrode or an electric field up to it, these negative charges would bend towards the positive plate. Well, why would they do that? Because opposite charges attract. If negative charges are coming out of there, they're going to be attracted to that positive electric field. And that's the cathode ray experiment. Okay, moving on. Our friend Ernest Rutherford, he probably had more than any other scientist. He gave more to the atomic theory. And he discovered the nucleus via the, we call this the gold foil experiment, or sometimes the alpha particle gold foil experiment. And this experiment said this, that an atom's mass is mostly in the nucleus. Over 99% of the mass of the atom is in the nucleus. The nucleus has a positive charge, right? So the charge of the nucleus is positive, and we'll talk about that as the year goes along. And then atoms are mostly empty space. That's really important. And then finally, one thing he was actually wrong on was that electrons are in fixed orbits. And we'll look at that with this picture right here. This picture, right? So this was Rutherford's picture of the atom. He said that the nucleus was positive, and you see it in the middle there. And then all these orbits going around the atom, electrons would revolve around the nucleus on that. That's not exactly how it works, but again, Rutherford did a lot to build the theory of the atom. So his gold foil experiment, real quick. So this is a particle emitter. This emits positive charges. We call that an alpha particle. And what happened was that these positive charges are shot through this gold foil. And most of them, 99% of those positive charges, went right through, right, in a straight line. And that's how Rutherford said, it looks like the atom's mostly empty space, right? Because most of the time it was going to go straight through there without hitting anything. But sometimes you see these arrows that are deflection arrows. Sometimes that alpha particle would deflect off something. And what would it deflect off of? Well, it would deflect off the nucleus of the gold atom. Why? Because if this is a positive particle and the nucleus is positive, we know that like charges repel each other. They go in opposite directions, and that was how Rutherford discovered the nucleus. Okay, our friend Niels Bohr pretty much took Rutherford's idea and he created the planetary model, that the nucleus is surrounded by orbiting electrons, but he added different energy levels. You see here that our first shell here, that would be our first energy level. Here's our second energy level, and here's our third energy level. As we get further away from the nucleus, our energy levels increase and our energy increases because of that. He was still talked about the idea that electrons have definite orbits, and we'll see that's wrong. But again, our next person is going to be our last atomic idea here. And this is Schrodinger and Heisenberg, friends who worked together in the lab, and they came up with the quantum mechanical model. And this is the current model we use today. And they said that electrons are in what we call probability zones, called orbitals, not orbits. And we really can't determine the location of an electron. They also started talking about the particle and wave theory of electrons. This is Einstein type of stuff. This gets into particle physics. It's pretty deep science, but I like this picture quite a bit. This is not 3D, but this shows you down here that we see kind of the density, how many electrons are in these fields. As we get closer to the nucleus, we have more electrons, and as we get farther away, we have less electrons in these orbitals. So this is Schrodinger and Heisenberg. This is the quantum mechanical model.